Hi, my name is Saba. I will be presenting our work titled FrisBE Adaptive Bitrate Streaming of Immersive Tiled Video. My co-authors are Ari Hauranranta, Igor Korcheo, and Emre Aksu. I will be briefly talking about the motivation and background for this work, the FrisBE method, experiments and the results, and finally conclusions and future work. So let's start with the background and motivation. We started with trying to build an ABR algorithm for the Nokia OMAF player. This is a publicly sourced player engine for the MPEG OMAF standard for 360-degree video. We decided to use tiled viewport dependent streaming, so a higher quality viewport and lower quality tiles for the non-viewport. The reason is a significant amount of bandwidth savings using the tiled viewport dependent streaming. And finally, we wanted to reuse existing ABR algorithms. There is years of research behind these ABR algorithms. They are widely deployed, and we wanted to find a way to bridge existing -ABR applications to 360 video. So in the first iteration, which did not work so well, we use the Nokia OMAF player, which requires that all tiles of a signal segment are available before playing. This maintains continuity of the viewing experience. We used a single instance of the ABR algorithm, which made a decision for all the tiles together, considering the full sphere. This also prevents different tiles from being at different quality. The player can calculate the required bitrate of the full sphere based on the advertised bitrates of the individual tiles. And the calculation was done once in the beginning, so for the initial viewport. So the tiles in the viewport at viewport quality and the tiles in the outside the viewport in the background quality or the lowest quality. And then for different quality levels, you know the full sphere bitrate, and you use that with your ABR. The reason this did not work so well is that depending on the content, complexity, and the sizes, some tiles might have a much higher bitrate requirement than others. We used ABR schemes for encoding our tiles, and also in addition to this, during head motion, the number of tiles in the viewport can change significantly, from as few as 2 tiles if you have larger tiles in the horizontal area, for instance, and as many as 5 tiles. Or more, depending on your tiling grid. So over here in this chart, we illustrate this phenomenon. We used this is for one of the test sequences that we used in our experiments, and we used different head orientations given here, 8 horizontal head orientations. So for instance, H1 is looking straight ahead, H2 is slightly towards the left, H3 is further left, and so on. And for each one of these horizontal orientations, you have a different set of tiles in the viewport. And then we had 3 vertical orientations. So blue would be looking straight ahead, for instance, and orange would be looking down, and or gray would be looking upwards. And you can see that the full sphere bitrate for the viewport tiles at a high quality and the background tiles at a low quality based on the advertised bitrates for each of the tiles, you can see that the full sphere bitrates are significantly different. This is one of the lowest, and this is one of the highest here, as high as 60 and as low as about 20 over here. So this is the challenge, and hence we came up with the FrisBE method. So the basic operation of the FrisBE method consists of 3 steps. In the first step, we find a representative viewport, which will be used for the estimation process. In the second step, we calculate the full sphere bitrate for the different quality levels for the tiles. And in step 3, we reuse an existing ABR algorithm with the calculated bitrates to adapt to network requirements. So let's go deeper into step 1. So over here we are showing a tile grid for a video, a simplified tile grid. The gray area is the viewport. So size of the viewport is known, and you can see that at this particular location, the 4 highlighted tiles will be in the viewport, and they will be downloaded at a higher quality, and the rest will be downloaded at a lower quality. Now we move this viewport in granular steps, and until we reach a position where the combination of tiles in the viewport changes. As you can see now, there are 6 tiles in the viewport, and this will be our viewport 2, so the second candidate. And now again we moved it further, and now there is another viewport orientation where we have a different combination of tiles. So we calculate we find these different orientations and these different associated viewport or a set of tiles in the viewport that we use for finding the representative viewport. Um, so once we have these viewports, for each of these viewports, what we do is we calculate a full sphere bitrate. And how we do that is that we use, let's suppose, the highest quality for the viewport tiles and the lowest quality for the background tiles, and we have a single value for each of these viewports. And then we find the representative viewport as the viewport which with a particular percentile. So we have a list of bit rates for the different viewports here, and then we use the particular percentile of these from this list to find the representative viewport. We use, for instance, in our implementation, the median. Of course, there can be other percentiles, the 75th percentiles or the 90th percentile, and more iterations with different content can help us find a more suitable value for this representative for choosing this representative viewport. So in step 2, once we have the representative viewport, we calculate the full sphere bitrate for each quality available. So let's break this formula down. So on the left-hand side, we have the full sphere bitrate at quality Q, and on the right-hand side, we have the sum of the tiles within the viewport at quality Q, the bitrate of the tiles within the viewport, and we add to it the sum of the tile bitrates of the non-viewport in the non-viewport area at the lowest quality, 0. So this is a very basic formula. So we have a fixed size viewport. We always use the lowest quality in the background and nothing else. However, this can be made more complex. So for instance, you could add additional levels where you gradually increase the background quality further. So once you have achieved the highest quality in the viewport, you can still continue increasing the quality in the background so that the experience is better if there is more bandwidth available. Or you could use different sizes of the viewport. So you can introduce a larger viewport so that the motion to high quality delay when you move your head is low. So this can be made more complex to include more levels. Regardless of how you do this, at the end of step 2, you will have a list of ascending quality levels and the bit trace associated with them. And these can be fed into an existing ABR algorithm, and with some slight modifications that may be needed. For instance, especially in calculating these indicators. For instance, I mentioned one here, which is that we considered for the buffer level for all tiles. So we considered the tile with the lowest buffer level to be used for the estimation of the next quality for choosing the next quality level. So now we can look at the full pipeline. We have the dash manifest here, which provides a list of bit rates for different tiles at different qualities. So it's essentially a table with 2 dimensions, and then we feed this to the FS bitrate estimation process, which picks the representative viewport, and for that representative viewport it gives a list of quality levels, and for each quality level the required bitrate. The ABR algorithm is a black box, as can be any 2D ABR algorithm, and it has these ABR indicators that it receives from the video downloader, including buffer duration, the idle time, the time to download a segment, etc. And then based on these, it picks a value Q for the quality, which passes a sanity check. If the throughput is enough, Q dash will be equal to Q. And then it reaches the video downloader. The video downloader, once it knows the quality to download, it already has a mapping for each quality with the viewport, the V viewport, and V dash non-viewport tiles. And based on this, it will download the tiles in the current viewport at the quality for the viewport tiles, and the non-viewport tiles based on the current viewport, the non-viewport tile quality. The downloaded tiles can then be passed on to the video player. Experiments and results. So a bit about the experiment setup. We did some basic testing within HMD, and to find that everything was working correctly, and it was. And then we did extensive test iterations with a 2D rendering of the viewport area. We used 3 different test sequences with 3 types of content. Each sequence was at a different resolution. So we had a 4K resolution, a 6K, and an 8K. And then we encoded all 3 of these in both a 4x3 tile grid and a 6x4 tile grid with different bitrate levels. The network conditions we emulated with the stable network conditions, which stayed the same throughout different levels of these stable network conditions. And then we also did changing network conditions where we dropped the bandwidth from very high rate to very low, and then from low to high. And in another one, we did gradually decreasing the bandwidth from a high level to a low level, and then gradually increasing it. We also used head motion during these tests, so we did the testing with no head motion, with only horizontal head motion at various speeds, with fast random head motion in different directions, and a human-generated head motion where we asked a user to actually view each of the content, and then we had content-specific head motion that we recorded during this viewing and then reused during our testing. So the results were promising in terms of stall events. We observed 0 stall events for stable network conditions with or without head motion. For unstable network conditions, we primarily observed stall events when the bandwidth was not sufficient. We observed under 1 second of stall events for unstable network conditions, so less than 1 second, when bandwidth was sufficient, and this was when bandwidth dropped suddenly. And however, this was under 1 second for a 10-minute video, so these were quite rare and were not very long. Finally, we observed that the viewport quality under stable conditions was similar for at least 2 of the sequences, with or without head motion. So it did not significantly alter the viewport quality when the user was moving their head. So conclusions and future work. We found FriSBE to work well with 2 existing algorithms. We used the BOLA algorithm as it is implemented in the Dash.js player. We modified it to work with our Nokia OMAF player, and then we used one of the existing time-based algorithms that has been built at Nokia. And the work, and we found that both of them, the results that we presented were considered both the algorithms, and they worked pretty well. The work is still, however, preliminary. We have identified some areas of future work in the paper and also during this presentation, for instance, optimizing the method for finding the representative viewport, and also further work in creating more quality levels for calculating the full sphere bit rates. With this, I would like to conclude. Thank you very much for listening, and we look forward to your questions and comments.